Okay, in this video we're going to go over a 6.2, and this will be on Riemann sums, and we're going to talk about finding the area under a linear curve initially between the curve and the x-axis using geometry. So all of case 1 is going to be using geometry. So look at our example below. We want to consider the horizontal line y equals 2, so that's the line, and there it is right there. And we're going to restrict the domain of the function, those are the x values, to -2 to 2. So here's -2, here's 2, and we want to figure out the area of this region using your knowledge of just basic geometry. So what we're going to do, we're going to look at this and we're going to say, oh, that's just a rectangle. A rectangle's area is going to be length times width. So what will the values be? Our length goes from -2 to 2. So that is 4 units. So this is 4 units from here to here. And our height is from 0 to 2. So that's 2 units. So therefore my area, so the area of this rectangle is going to be 8 units squared. Alright, that's using basic geometry. I have nice straight lines. I have no need to worry whether I have that correct or not. It is just perfect. Okay, let's go on to the next example. Alright, in this example we also have a shape, and I have nice straight lines. This time my function is 2x, and it's this line right here. And the domain restrictions take us from, they're right here, they take us from 1 all the way to 3. So there's my shape. It's up against the x-axis. I want to find the area of that shape. So I'm going to make this a triangle and a rectangle stacked. Okay, our width this way is 2, and this is also 2. So that means I have a rectangle of 4 square units. My triangle, this height is 1, 2, 3, 4, and its base is also 2. So the area of a triangle is 1/2 base times height, or 1/2 4 times 2. 4 times 2 is 8. Half of 8 is 4. So this area is 4. At the bottom of this page, we start talking about the different ways we can represent this symbolically. So I know it equals 8. Let's go down and see how I'm going to represent this symbolically on the next slide. Okay, I want you to look at the bottom of your page, and I want you to notice that you have the following. Here on your endpoints, 1 and 3. This is 1, this is 3. Then you have a function right here. That function is called the integrand, and you can see that word at the bottom of your page. Your integrand is the function 2x. I write that right here. Because my function is written in the variable x, I write dx next. So this is how we're going to express this, and then it's going to be equal to the number we just got. And when we divvied this up, I believe we got 8, so that's how I express my answer using math language. So just to recap, here are your endpoints, here is your integration symbol, here is your integrand. This tells you the differential of the variable. It tells you that your function is in the variable x, and here is your area. Okay, so you want to know all that vocab, and let's move on to the next page. Okay, in this slide or this page, example 3, I also have a function that I could estimate the size of by using geometry. So this is the last one we're going to do. So we're going to use our geometry to break this up into one big old rectangle, which has an area of 12 square units. I'm going to let you figure that out. This is 4 plus 2 more is 6. This is 2. You should be getting 12. And then this little triangle, this is 1. Right here is 1. Here's 2. 1/2 1 times 2 is 1. So the area of this shape is going to be 13. So I'm going to say the area equals 13, but we're able to express this in a different way. They didn't give us a function that we're used to seeing where you have actual numbers. They gave us a notation for a function. So since that's all I have, if I ask you to express this using the proper notation, you would have the integral symbol, you would run it from -2 to 4, you would have your h of x, which is your integrand expression, behind the integral symbol, you would have dx, which is your differential of variable, and then that would equal 13. Okay? So those are all case 1 where we have a geometric shape that we can just divvy up between rectangles and triangles and use our geometry knowledge and find the area under the curve. Okay, now we're going to go next to curves that you don't have that luxury. So let's see what our procedure will be for that. Okay, here we see our first curve. I have still straight sections here and here where the endpoints are. I see that I have shaded where I want to figure out the area, but this time I don't have a straight line for the curve. I have a parabola section, so therefore I'm not going to be able to do my straight lines and get my area. So I have to figure out another procedure, but we don't know it yet. So let's do the following. Let's use our notation to express what we do know. Here's our integration symbol. Our domain restriction goes from -1 to 2. Those are my endpoints. Our integrand is the function behind the integral symbol. It is 1/2 x squared plus 1. You would not use the y equals. Because it's in terms of x, you would write dx, and this is going to equal some number which is still unknown. So you should be able to recognize that you can't use straight lines again, but you can express it using our new notation, and you can read it out loud using our new vocabulary. The one thing I would add is I'd probably put parentheses here so that I can see that that's my entire function. So let's move on to the next page and figure out what our technique's going to be when we have these curves. Alright, here is our new technique. It's called Riemann Sums. Riemann Sums is going to be used to approximate the area between the curve and the x-axis. So at this point we don't know the rules of integration where you can get an exact answer. So we're going to use Riemann Sums as an approximation tool. So I'm going to teach you right Riemann Sums and left Riemann Sums, and then we'll talk about what this does for us and how we can work with these problems. So first off, I give you some written direction right here. I'm not going to read it to you, but I'm going to do that as I solve this problem. Okay, the first thing you would do is you would put this function into your y1 in your calculator. So this goes into your y1. Then, if you did not have this table, you can get this table by using your graphing calculator, saying second table set, starting at -1, so -1 is your start. Your change in x is going to be 1, just 1, so delta x is 1. The other two questions should be auto, then go to second table, and you should be able to see where I got these y values. The y values are very, very important. Alright, let's start with our left Riemann sum. Left Riemann sum means I'm going to build a series of rectangles, and I will start at the left domain value. So starting at the left domain value, I'm going to change my color so you can see it a little bit better. I'm going to come up, I'm going to hit the curve, so I've come up, I hit the curve, which is the function, I go to the next increment, and I come down. That's my first rectangle. I then do my second rectangle. I start at 0, I come up to the function, and I go horizontally across, and I come back down. That's my second rectangle. We're going to use 3 rectangles to estimate the area under this curve. Next, I go to 1 value, the 1 value for x. I come up. Okay, let me just do that again. Okay, can I go back? Okay. All right, so I'm going to go up, hit the function, go across to the next x value, and go down. There's my third rectangle. So you can see, so let's just color in some of the places that we're missing or that we're overestimating. So you can see that our rectangle is a little bit higher here than our function actually is. Our rectangle is a little bit lower here, and it's a lot lower here. So we can see that this is not going to be an exact estimate. In fact, it looks like it's going to kind of be I would say, an underestimate, because there's a lot more yellow above that I'm missing than there is below. Okay, so now we need to figure out, well, what is the sum under this? What is the area? What is the sum of all these rectangles? So I'm going to change again back to our color. And what we're going to do is I'm going to say, well, what's this length for every single one of them? That length is the distance from -1 to 0, from 0 to 1, and from 1 to 2. That distance is always 1. Okay, so all of these are 1. Your height of the first rectangle is the same height as the y value at -1. Your height of your second rectangle is the same height as your y value when x is 0. Your height for your third rectangle is the same height as your y value when your x is 1. So what you're going to do is I'm going to add up these rectangles. So my left Riemann sum, is going to be the base, which is 1, times the first height, which is what I've circled above, which is 1.5, plus the base, which is 1 again, times 1, because that's the height that I've circled second, plus 1, that's your base, times the third height, which is 1.5. So 1.5, so here's the first rectangle, its area. Here's the second rectangle, that's its area. Here's the third rectangle. It looks to me like the area under the rectangles using Riemann sums is 4. And that is your left Riemann sum. Okay, let's go to the next slide, and we'll now do the right Riemann sum. Alright, what I've done for us is I've copied the table to this next slide, because I want to do right Riemann sums using the same table that I used for left Riemann sums. Okay, so right Riemann sums, as you can probably guess, we're going to start at the right endpoint. We started at the left endpoint last time, so let's do it in green. So if I start at the right endpoint, it's this endpoint right here. Okay, I hit the curve, and I go over to the next x increment, and I come down. That's my first rectangle. I go for the next one. I am starting at 1. I hit my curve, go over horizontally, and come down. That's my next rectangle. I go up, I hit the curve, go over horizontally, and come down, and that's my third. So in all these cases, the number of rectangles is 3, so we would say n equals 3, but that's coming soon. Let's figure out what this area is. So we used the first 3 values when we did left Riemann sum. So we're going to use not the first 3, but the last 3. So we're going to go here, here, and here. I'm going to circle the y's because they're the most important. Okay, we know the base of each of these rectangles is 1, so I'm going to write a 1. Okay, so the last rectangle has a height of 3. So this is 3. So my area will be, and we'll start from the right, so 1, which is your base, times 3, that's your first rectangle, plus, look at our next rectangle, 1 times a height of 1.5, plus our next rectangle. It's all going to have a base of 1, times the last rectangle has a height of 1 as well. Okay, so there are our 3 rectangles. Let's add these up, knowing that we got 4 last time. So I have 3 plus 1 is 4, and this is 5.5. So this time my area is 5.5. So that's higher than the 4 we had before. So, and let's talk about overestimating and all of those good things again. So I'm going to turn to my yellow again. So this first rectangle on the left here is an underestimate by that much. The next rectangle is an overestimate by that much. And the last rectangle is an overestimate by this much. So we're seeing we definitely have an overestimate. One way that you can approximate the area is to take the average of these two measurements. So you would say 4. So I would say 4. Let me change color because you're not going to be able to see the yellow. Okay, so 4 plus 5.5 divided by 2 could give you an idea of what's the average. So I think when you add those two together, you're going to get 4.75, but we'll do that on the next page. So that average is not great, but it is a method that we can use to approximate the area under the curve. Clearly, the left and the right are not really on target, so maybe the average is not that on target either, but it is a method that we could use. So let's go on to the next page and we'll fill in some of this information. Okay, here we're just filling in the information from the previous page. So the left Riemann sum was 4, the right Riemann sum was 5. Here's how you would write it, and if I ask you to give me an approximation, one thing that we can use, and what I'm going to expect you to use for Riemann sums, is to get me the average. So to say 4, which is the left Riemann sum, plus 5.5, the right Riemann sum, divided by 2, if you do that math, you get an average of 4.75. Not perfect, but good enough. Okay, in this particular situation, looking at the yellow areas, the left Riemann sum is the lower of the two Riemann sums, and the right Riemann sum was the upper of the two Riemann sums. This terminology is not that important for our study here, but I'm just pointing out that one was greater than the other. Okay, we're going to look at finding the left and right Riemann sums of a different shape, and we'll do that on the next page. Alright, here's our next page, and this time I'm giving you some more information about doing Riemann sums. You don't always have exactly increments that are one unit or one space apart. The way you figure all this out is you have a little formula. So remember that when we had the integral symbol, the endpoints were on either side. The lowest one was here at the bottom, that was your A, and the highest one was here at the top, that was your B. So what they're saying is when you're asked to do a Riemann sum, you're going to be told how many rectangles to use to do your approximation. So you can just envision having a whole bunch of rectangles and just cutting them smaller and smaller and smaller to the point that in the limit, the base of that x value, that base, is going to be just about 0. Okay, that's what when we approximate things using the techniques we learned in 6.1 and 6.3, actually doing anti-differentiation. But in this section for Riemann sums, we're just doing approximations. But you can see that you would get a better approximation if you had thinner and thinner rectangles, because more of them could fit under the curve and you would have less of an error. So keep that in mind. So here we have a problem, and they want us to figure out what is the left Riemann sum, what is the right Riemann sum, and then we can kind of take the average to get a better, maybe a little better estimate of what the area under the curve actually is. But in this situation, I'm going to tell you that they want us to use 4 rectangles. So here's our little formula. You take your 2, which was your B value, this is B, this is A, minus the 0, which is your A value, over 4. Okay, that ends up being 2/4 or 1/2. That is your delta x. So if I need to go up by 1/2, I'm going to go into my second table set and I'm going to say I'm going to start at 0, and my delta x, so in this case your delta x, will be 1/2. Then go to second table, and you'll be able to fill in the rest of this table because your table should look like this table. So where I have this question mark, you should see 3.75. Now you may need to change your mode, so to speak, off of float and onto 2 decimal places if you're not seeing 3.75. Under 1.5, I am getting 1.75. Okay, so I need these y values because they're really important to figure out my Riemann sum. Alright, if my increments are going to go up by 1/2, let me change my little color, and we'll say this is the half between, whoops, let me cancel that. This is the halfway mark between 0 and 1, and here's the halfway mark between 1 and 2. And so I'm going to have these vertical lines here that will go up to my curve, here, and I have this one here, and I have this one here. Okay, so I can see the vertical lines and then the other one starting over there. So let's do our left Riemann sum. So I'll pick a different color. Why don't we do this in blue? Left Riemann sum, you start at the leftmost endpoint, which is 0. You go up to the function, which ends right here, and you go horizontally across until you hit the next vertical section. Right here in blue is my first rectangle from Riemann sums. To do the next one, I go up, I hit the curve, I go across horizontally, I hit the next vertical x value, and that's my second rectangle. Remember, I'm getting 4. Okay, now we're going to go up to, this is 1 right here. Go up to 1, hit my curve, go across, come down. Third rectangle completed. Fourth rectangle, I come up from 1.5, I hit my function, go horizontally across, and come down. That is left Riemann sum. Can we figure out what all the rectangles are? So this would be my suggestion. Circle, if you're doing left Riemann sum, I'm going to use this y value, this y value, this, and this. It's always one less than the number of places you have. So let's do it a little fancier now. Since you know that your base, every single one of these delta x's is 0.5 or 1/2, why don't we say left Riemann sum, and let's factor out the 1/2, and then we're going to add up 4 plus 3.75 plus 3 plus 1.75. Add those numbers up, multiply by 1/2, and we should get a left Riemann sum of 6.25. Okay, let's do the right Riemann sum. Okay, right Riemann sum, why don't we, well, I think I'll leave everything in blue since I can still contrast it with now my red. Right Riemann sum, I'm going to start at the right endpoint, and when I hit the curve this time, I don't have any height. So here's my first rectangle. Look, it has no height, so it's going to have an area of 0. Here comes my second rectangle. I come up, I hit my graph, I go horizontally across to the next x value, and that's my second rectangle. My first rectangle really didn't exist. I come up for my third rectangle, I hit my function, I'm working in red here, and I go across, and I can come back down on my next x value. To get my last rectangle in red, I'm going to come up from the x value of positive 1/2, hit my function, and come across right here, and come back down. Okay, I'm going to circle the y values I'm going to use this time. 0, 1.75, 3, 3.75, and I'm not doing the last one because remember you're always going to omit one. So if I'm going to do my right Riemann sum, so I think I'm going to do this up here. So right Riemann sum, I know my base is always 1/2, so have a 1/2 out in front. Then you're going to add up 0 because that first rectangle had no height, plus 1.75 plus 3, which is the next y value, plus 3.75. When you multiply each of those by 1/2, you should be getting a right Riemann sum of 4.25. If you wanted to get the average of those two, you would add it together, divide by 2, and I would get approximate area of 5.25. In this situation, which was the upper one? So the upper one in this situation was the left Riemann sum, and which is the lower? In this situation, it ended up being the right Riemann sum. And you won't know that until you look at your answers for the left Riemann sum and the right Riemann sum. Okay, so that's our first big lesson here. Let's turn to the next page now. Okay, so let's look at this. Here we have the expression written in math notation, and we're going to say that the average is what we're going to report as approximately the area under that curve. Be able to write this and know your vocab words. Okay, let's do a couple of these. I have it set up. You would put in your graphing calculator for number 1, y1 equals x squared. You would go to your second table set, and you would think about what we're doing. We're going to start at 1. What are our increments going to be? We know that the delta x, so delta x is going to be b minus a, so that's 4 minus 1 over 3. So that's 3 over 3, which is 1. So that means my x table will start at 1, and my delta x, so let me cancel that, my delta x will be 1. So I'm going to say 1, 2, 3, and 4. Remember, I'm using 3 rectangles, so I should have 4 boxes. You should get the following numbers: 1, 4, 9, and 16. Okay, so let's look to do right Riemann sum. Well, excuse me, to do left Riemann sum. This is what I'm going to use. So I'm going to say 1 times 1 plus 4 plus 9, so that's 1 times 14. That gives me a left Riemann sum of 14. Switching colors. To do right Riemann sum, I'm going to use these boxes, and I'm going to say my base is still 1 because that's the distance between all of my x's, and I'm going to use 4, 9, and 16. So 1 times 4 plus 1 times 9 plus 1 times 16 should give me 29. If I add these together, divide by 2, I will get 21.5. The right Riemann sum is the upper in this situation, and the left Riemann sum happens to be the lower in this situation. Okay, so let's do a couple of more. We probably won't do all of the examples, but you'll get the gist of it. Okay, in the interest of time, I'm just going to tell you that if you only do the left Riemann sum for the second problem, you should be getting 14. See if you can fill in this table using your graphing calculator the way I explained in the last problem. Alright, moving on. Number 3 and number 4. Number 3 asks you to get right Riemann sums, and number 4 asks you to get average. So to get average, you would say left Riemann sum plus right Riemann sum over 2, and that gives you the average. Let's do number 3 together. Okay, you don't have a grid, you're going to need a grid. So let's figure out what our x's are going to go up by. The way you figure out your delta x is you say b, which is 3, minus a, which is 0, okay, 3, 0, all over number of triangles, which is 3. So your delta x ends up being 1, which is what we had last time. Don't always expect 1. Always do that little formula. So if these are my x's and my y's, and I'm going to go up by 1, and I'm going to start at 0. So that's going to be 0, 1, 2, and 3. You would then go to your graphing calculator, set up your table the way we spoke about. So I'm getting 16, 15, that's a 15, 12, and 7. So if I do right Riemann sum, my increments are 1, so 1 times, okay, right Riemann sum means that I'm going to use these values to get my 3 rectangles. So 1 times 15 plus 12 plus 7, because remember I'm getting areas of those rectangles, and you should be getting for number 3, so this is number 3, you should be getting a value for right Riemann sum of 34. Alright, so I'm going to let you be able to do 4 on your own. Your average should be about 3.99 for 4, but we're not going to do it together because I want to keep this somewhat short. I'm already at 31 minutes, and I want to go over the velocity functions because they are very, very important. So let me do that on the next page. Alright, we haven't really talked about Riemann sums or area under the curve as working backwards, and that's what I want to do now. So if you know your area under the curve is the area under the curve of velocity, when you integrate that, you get back the position function. Remember, if you take the derivative of position, you get velocity. Take the derivative of velocity, you get acceleration. Well, working backwards, I can figure out if I know I have an interval from hour 0 to hour 6 of a velocity function, and I want to figure out, okay, between these hours, 0 and 6, how far did this car go? I can do integration, and that will allow me to get the total mileage, which is the distance. So start thinking about Riemann sums and getting there into the curve as working backwards. Okay, so that's the idea that we're going to handle right now. So let's look at the next page, and we'll talk about filling in the chart and answering some questions, and then doing right Riemann sum and left Riemann sum and getting the average, and understanding that that average is going to be the distance traveled over the time interval, because when you integrate and you approximate this integration by Riemann sums, you get back the original function. Okay, so that's some underlying premises that will be addressed throughout this chapter. So let's go to the next page. Okay, so this is the table that's below the graph on the velocity page. And so what you would need to do is you can say 6 minus 0, and how many rectangles did I want? Well, I guess since they gave us the table, we're just going to go ahead and fill in the table. So I can see that my x is going up by 1s. So when I do second table set, I'm going to start at an x value of 0, and my delta x will be 1. Then go to second table, and you can fill in the values that you should be seeing. And those values should be, this should be a 55, this should be a 27.5, we're taking everything to the nearest tenth, so this should be a 19.4, I think it is. Then I should have a 9.72, so that's out to the hundredth, so that was not consistent, so let's just make that a 9.7. And then the last one will be a 6 point, it was 8.8, so it's going to be a 6.9. So that's our table. Remember, the y value is velocity, the x value is time. So the first question says, what was the velocity of the car at the beginning of the interval? So the beginning of the interval is at time 0, right here, and the velocity was 55, and this is miles per hour. That's your velocity. Okay, then they ask you, what about at the end of the interval. So the end of the interval is right here at 6 hours, and that velocity was 6.9 miles per hour. Okay, next they want you to figure out the integration by using average Riemann sums. That means you've got to do left and right. Okay, I'm not sure what this is. We'll get rid of that. So let's set up our equation. Okay, so it's not VT. We actually have a function. So our function is going to run from 0 to 6, and it's going to be 55, and then I'm going to have a 2, and that 2 is raised to the negative t over 2. If your variable is t, do not write dx. You need to write dt. Okay, so I'm going to do the following. I'm going to change color. Okay, your left Riemann sum will start here and we'll go up to this second to last box. Okay, so your left Riemann sum, your distance from all the x's is going to be 1. Then I'm going to pick 55, 38.9, 27.5, 19.4, 13.8, and 9.7. And I'm going to sum them up. So I'm just going to call that the sum. That symbol means sum. And when I do that multiplication, I am getting 164.37. So you should get about that, assuming that I've rounded correctly and that I only took things to the nearest tenth initially. Okay, next, our right Riemann sum. So we'll change colors. Our right Riemann sum will still be 1, because that's the base, and then times the sum of the blue. So I'm starting out here. Here's my 6.9, 9.7, 13.8, 19.4, 27.5, 38.9. Don't do the last one. Okay, there are our numbers. So I'm going to say 1, and we'll call that the sum of all those y's I just circled. 1 times that, because 1's the base, and I'm getting an answer for a right Riemann sum of 116.18. Okay, if I want to average those, I add them both together, divide by 2, and my average is going to be what I'm going to say this is equal to, 140.25. And what is that? Since I was dealing with miles per hour, when I take the integration, I go back to the previous function, which was distance. So I have determined that in the hours from time 0 to time 6, I have traveled 140.25 miles. Okay, we have a couple of more things to talk about. And so let's continue on this journey. Okay, we're going to do one practice problem on this page, and we're going to do practice problem number 1. There's more for you to practice. So here's our function. If I were to use my nice notation, I would say I'm going to run my velocity from 0 to 30, because I'm reading what the table is telling me. Here's my function, 16t, because it's in terms of time. I'm going to say dt, and I want to get an average area under the curve. Since I have velocity and it's in feet per second, I will get a distance for my answer, and that distance will be in feet. Okay, so you should be able to fill in this table. You are going to start, so go to table set. Your x is going to start at 0. Your delta x, looking at this, is going to be 6. So to do your left Riemann sum, well, okay, so then you get your table. Go to second table set, fill these in, then go to second table, and you should be getting 0 here, 96, 192. If you cannot get these numbers, definitely come see me or ask one of your friends, because this is key to be able to do this. So you are clearly going to need a graphing calculator for this whole section. Make sure yours is all charged up. Okay, so there are our values. So let's do left Riemann sum. doing left Riemann sum, I'm going to take from the left, these skip the last one. Okay, to go left Riemann sum, what's my distance from between every x? It's 6. Then sum up 0 plus 96 plus 192 plus 288 plus 384. So that's giving us 1, 2, 3, 4, 5 rectangles. So by the way, n will equal 5 in this situation. Doing that math for the left Riemann sum, you should get 5760 feet. Okay, doing the same thing for now right Riemann sum. Changing to green. Right Riemann sum will be this way. So to do right Riemann sum, what I'm going to do is I'm going to say 6 is still my base. Now I'm going to add up 96 plus 192 plus 288 plus 384 plus 480. Notice I didn't pull the first one. So I have 1, 2, 3, 4, 5. That's my n. I'm correct. If I do that math, I will get 8640 feet for an answer. If I then add the two together and average them, I will get an average distance of 7200 to give me a rough approximation of the area under the curve. The key is that if you have a function that's velocity, and that's what you're integrating under the curve, you get back the original function, which was the position function, and your units are feet. So be clear about that. I'm going to just briefly talk about the next page, and then that'll be it for this video. Alright, on this page, the important takeaways are these. If I give you marginal cost for your function that's going to be your integrand, so if you integrate marginal cost, which is 50 minus x, and I'm going to integrate it between 0 and 20, and I say dx, you will get back total cost. Alright? Because this integrand is marginal cost. Since when you take a derivative, when you take the derivative of total cost, you get marginal cost. When you take the antiderivative of marginal cost, you get total cost back. Okay, and the last thing I'm going to say is this. If you have marginal revenue, so setting this up, this is 1.5 plus 0.2x. I'm running it from 0 to 30. You should be able to do this. I have dx because everything's written in terms of x. If you take the antiderivative of marginal revenue, you will get total revenue. If you take the derivative of total revenue, you will get marginal revenue. So be aware of that so that you understand what you're getting back. So total cost is going to be in money. Marginal cost is money per unit of time. Total revenue is going to be in money. Marginal revenue is going to be money per time. Okay, so be clear about that and you're set to go.